Here's the trap that kills students on the AP exam every single year. You know electron configuration cold. You can write out iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, no problem. Then the question asks, what's the electron configuration of Fe2+? And you write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. You removed 2 electrons from 3d, logical, right? Wrong. And that one mistake costs you points on multiple choice and free response. Today we fix that, and we go deeper into why the periodic table is literally a map of electron configurations. Let's start with the architecture. 3 rules govern how electrons fill orbitals. Aufbau principle. Electrons fill the lowest energy orbitals first. Pauli exclusion. No 2 electrons in the same atom share all 4 quantum numbers, which means each orbital holds at most 2 electrons, and they must spin in opposite directions. Hund's rule. Within a subshell, electrons occupy separate orbitals before pairing up. 1 electron per box before you double up. Always. Why does Hund's rule exist? It's not arbitrary. Electrons repel each other. They're all negatively charged. Spreading out across degenerate orbitals minimizes that repulsion. The atom is lower energy when electrons stay apart. The exam tests whether you understand this is an energy minimization principle. Now the filling order. You've seen the diagonal arrow diagram. The sequence is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. Notice that 4s fills before 3d. Why? Because at the point of filling, 4s sits at a slightly lower energy than 3d. This is the fact that everything else hinges on, and it's also the source of the biggest mistake students make with ions. We'll come back to it. And it's also the source of the biggest mistake students make with ions. We'll come back to it. Here's the nuance. Once 3d orbitals start filling, electron-electron repulsion and shielding shift the relative energies. In a completed transition metal atom, 3d is actually lower in energy than 4s. So when an atom loses electrons, it loses them from 4s first, the highest n orbital, not from 3d. This is not a trick, this is physics. In a completed transition metal atom, 3d is actually lower in energy than 4s. So when an atom loses electrons, it loses them from 4s first, the highest n orbital, not from 3d. This is not a trick, this is physics. Let's answer that spark directly. The common misconception is, last in, first out, like a stack. If 4s filled last before 3d, shouldn't 4s electrons leave first? Actually, that reasoning accidentally gets the right answer for the wrong reason, and it breaks down the moment you try to explain why on a free response. Here's the real mechanism. The energy ordering of orbitals is not static, it shifts with nuclear charge and electron count. Once 3d electrons are present, they repel the 4s electrons, pushing 4s to higher energy than 3d. So in Fe, which has a full atom configuration, 4s is now higher in energy than 3d. When ionization happens, the highest energy electrons leave first. That's 4s. Fe, R, 4s2, 3d6, Fe2+, R, 3d6. Remove both 4s electrons, not from 3d. Fe3+, R, 3d5. Now you've removed all of 4s and 1 from 3d. Notice Fe3+ has a half-filled 3d subshell, 5 electrons, 1 per orbital. That's extra stable. Some AP questions will hint at stability of half-filled and fully filled subshells for this exact reason. Now let's connect electron configuration to the periodic table structure, because the table is the configuration. The s block is groups 1 and 2, valence electrons in s orbitals. The p block is groups 13, 18, valence electrons in p orbitals. The d block is the transition metals groups 3 to 12, filling d orbitals. The f block, your lanthanides and actinides, filling f orbitals. The period number tells you the highest n value in use. From this, every periodic trend follows directly. Atomic radius decreases across a period. Same energy level, but more protons pulling in. Atomic radius increases down a group. New energy levels, electrons farther from the nucleus. Ionization energy is the inverse of radius. Smaller atom, higher IE, harder to remove an electron. Electronegativity follows the same pattern. These trends aren't separate facts to memorize. They're all consequences of the same variable. The ratio of nuclear charge to electron shielding, which we call effective nuclear charge, or Z-eff. 1. Electron configurations follow Aufbau, Pauli, and Hund's rule. But these rules exist because electrons minimize energy and repulsion. Mechanism first, rule second. 2. When transition metals form cations, 4s electrons are removed before 3d. Write the neutral configuration first, then strip from highest n. 3. Every periodic trend, atomic radius, ionization energy, electronegativity, is a direct consequence of effective nuclear charge. More protons, same shield. Electrons get pulled harder. That's the one idea behind all three trends.